Welcome back to Valiant PE. Today's topic, bolted joints, the critical fastener. All right, so like usual, we're going to go through a quantitative problem. We're going to solve it together. Then we're going to go break it down and see what makes it a PE level problem. So let's get into it. First thing I do anytime I start a problem is I want to breathe deep. You got 80 questions to go. Take a second, breathe deep, read the problem, and then write what you're solving for in its units. Here we go. A bolted pipe connection experiences a bending moment, as shown. If bolt A is removed, what is the percentage change in the force carried by the critical fastener? Neglect preload effects. Bolts are evenly spaced. Okay, so we've got some answer information here. We've got some bolt information here. We've got a moment value. We've got some imagery that shows us what bolt A is. We've got some more imagery here showing the moment, and then also giving us some info about our bolt circle. I'm going to say we're solving for a percent increase in force, and I can tell from our answer choices we don't have any units. It's going to be percentage. So let's get to it. Step one. Let's look at the bolt distribution. The first thing we're going to do here is assume, just by looking at our picture, that our flange is uniformly stiff, has uniform stiffness. So we have no gussets, we have no reinforcement plates. Nothing about this joint is going to make any part of it more stiff than another part. Looking at the bolt distribution, we can see that it's symmetric about the horizontal axis and the vertical axis. And we know that this joint is subjected to a moment. So the things that are going to resist a moment are forces times distances. So each individual bolt has a force applied to it. It's going to carry a load, and we need to know what distance above the neutral axis each bolt is located. So let's start by looking at the distance from the neutral axis to bolt 3, D3, is equal to the diameter of the bolt circle over 2. That's just going to be the bolt radius. We're going to call that R, just an arbitrary value R. The distance for bolt 2 is this distance here. And the triangle that we're going to be drawing is essentially this. Radius, R, that's our D2, and this is alpha 2. Conversely, or similarly, D1, it's going to look something like that. R, D1, alpha 1. What is alpha 1, alpha 2? So alpha, let's zoom in here. This angle, that's our alpha 1. This angle, alpha 2. And by inspection, we can see that alpha 2 equals 60 degrees, alpha 1 equals 30 degrees. So let's solve for D2. That's the same thing as saying R times sine of alpha 2, which equals R sine of 60. And I'm going to leave it unsolved for the moment, and then same for D1, R times sine of alpha 1 equals R times sine of 30 degrees. So notice that this here is our neutral axis, and now we have solved for all the distances above the neutral axis, and it would be the same for below the neutral axis as well. All right, step 2. Let's look at the loading profile. Okay, so we know that this joint experiences a moment, M, a bending moment. So we have forces in the bolts that are going to be resisting this moment. So let's try to draw the forces in each one of these bolts. Force there, force here, and they're going to take the pattern of a triangle down to 0 about the neutral axis. Conversely, we're going to have the same thing, but in compression. Oh, I've drawn that wrong, excuse me. There we go. We're going to have compressive forces here, and here, and here. Okay. So now we're going to make another assumption. We are going to say that because bolts are intended to be loaded in tension, that only bolts in tension are going to be resisting this moment. Bolts in compression below the neutral axis are not going to fail. It's going to be bolts in tension above the neutral axis that are going to be stretched. That's what we're checking. So we're going to just assume, make an assumption here, that we are going to ignore the bolts below the neutral axis. Wow, okay, it undid those. Let's try that again. We're going to ignore all these bolts and say tension bolts only, forgot my N there, tension bolts only are the only items resisting the bending moment. Good. Next thing is, well, what are the values of these forces? We've got F3, F2, and F1. We don't know what they are. We're going to make another assumption here. We're going to say that, well, let's draw F3 for a moment. F3 is a distance r above the neutral axis, and it makes a triangle with an angle theta. Well, what about F2? We're going to say that F2 has a similar triangle. Distance d2, the triangle makes the same shape, thetas are equal. So we're going to write a mathematical expression treating these similar triangles as the same. We're going to write F over R is equal to F2 over D2. So that's our second big assumption here. We're going to use similar triangles to say that the bolts are going to carry a load in proportion to their distance above the neutral axis. Now we're going to go, let's evaluate this expression. Let's rewrite by plugging in some terms. F over R equals F2 over R sine theta 2, alpha 2. Now I should say before I move on, I have just assigned F3 the value of F, meaning it's our maximum force, max force. So every bolt below it is going to be in proportion to that maximum force. So I've just written F over R. Let's solve this expression, rewrite it a little bit further. F over R, F2 D2 over R sine of 60, plugging in for alpha 2. We're going to rewrite again, but in terms of F2. F2 is equal to F times R sine of 60 over R. R's cancel. F2 is equal to F sine of 60. The same concept applies to F1. We could say F1 is equal to F sine alpha 1 is equal to F sine of 30. Again, I'm going to leave these unsolved for right now. So two big assumptions here. Number one, bolts in tension only. And number two, the forces below the max force are in proportion to the distance above the neutral axis. All right. Now, let's write our equilibrium equation. We're going to solve for a sum of moments here. Sum of moments about the neutral axis. Just going to give an arbitrary direction there. Is equal to, F is equal to F3. F times R plus 2 times F1 times D1 plus 2 times F2 D2. Just to go over that one more time, we've got F times R plus F2 times D2, but there are two of them. There's this one and this one. And then F1 times D1, and again, we've got 2. 1, 2. All right, let's put some values to this expression. We're going to plug in what we've already solved for. F1 is equal to F sine of 30. D1 is equal to R sine of 30. And same concept for F2. Sine of 60 times R sine of 60. Great. Now let's simplify. Pull FR out. And I've got 1 plus 2 times 0.25 plus 2 times 0.75 equals M. Forgive me, I didn't write our M there. My bad. Now let's simplify a little bit farther, and we're going to say that this expression is equal to 3FR times M. And solving a little bit farther, F is equal to M over 3R. Let's put some values here. M is equal to 12,000 pounds force per inch. That comes from our problem statement. 3. And what is R? R here is going to be dBc over 2. 8 over 2 equals 4 inches. 4 inches. So inches cancel, and we are left with F equals 1,000 pounds force. Great. Now, this is our answer, sort of. 1,000 pounds force is the force that this bolt sees in normal loading conditions, this bolt right here. But what happens to that force when we come to bolt A and we get rid of it? That's what we're going to do next. All right, so we're going to rewrite the equilibrium equation. I have simply just copied this equation from the previous step. We're going to rewrite it by saying we have killed this bolt, so therefore we've killed this 2, and that becomes a 1. Now, write the expression again. FR times 1 plus 2 times 0.25, well, bad 5, plus 0.75 equals M. That comes out to the following. 2.25 FR equals M, with F equals M over 2.25 R. Put some values to it, 12,000 pounds force times inches over 2.25 times 4. We're left with 1,333 pounds force. All right, good. Here's another, oops, wrong tool. Here we go. Now we can see the load has increased. Let's go to the last and final step here, and we're going to compare old force to new force and get our percent increase. Our percent increase in force is equal to F new over F original. 1,333 pounds force over 1,000 pounds force. Pounds force cancels. We're left with 1.33, another bad 3. And that's going to give us 33%, which is answer A. There we go. There's our answer. Let's go back and take a look, make sure we did everything right. Yes, we can see there's answer A. Notice that we have a positive. There's a couple tricky answers, maybe a negative that might make you stumble a little bit, but we got the answer. Now, let's go talk about what makes this a P-level problem. Let's break it down. Okay, the first thing is you have to understand what the critical fastener is. And you need to be so familiar with this topic that you can look at that bolted joint by inspection and tell that the critical fastener is the one farthest from the neutral axis. The second thing is we need to understand the loading profile, which is very similar to a beam in bending. So if I have a normal beam here, just think normal beam theory here, simply supported beam, and I come through and I cut the beam right here, I can draw my loading profile. I'm going to have compressive forces on the top. That's my neutral axis. And I'm going to have tensile forces on the bottom. Now, that's very analogous to the situation we have here. We have, with our bolted joint, we've got a flange and a neutral axis, but we've got the reverse. We've got tensile forces that decrease in proportion down to 0 at the neutral axis. So the point here is be familiar enough with beam theory and beams in bending to know I'm looking at basically the same thing. The next thing we're going to look at is the bolted joint external load. So we made a couple assumptions here and said that the tensile bolts only were the ones we're going to consider, and by inspection you need to be able to tell that they're loaded in tension. The only way you're going to get here is by spending enough time reading about beam theory, solving enough problems to know. We're going to neglect preload, or excuse me, we're going to neglect the lower bolts because they're in compression, and we need to know enough about bolts to know that they're not designed for compression. None of the topics in the machine design book are about bolts and compression. It's all about tension. And we're going to neglect the stiffness of the clamped members. So there's nothing in here about how much proportion of the external load that the joint absorbs and how much does the bolt absorb. None of that here. All we're looking at is simple force. Now, the reason I bring this up is you need to be familiar enough with, say, like a joint diagram to know what you're not looking for. We don't care about preload, we don't care about axial stress. All we care about is force distribution. If you haven't looked at the critical fastener concept enough, you might get tripped up on, well, wait, they're giving me proof stress. What do I do with that? Do I need to know what proof stress is? Do I need the tensile stress area? They didn't give me a preload value. You don't need to worry about that. The next thing is you've got to be able to be very fast with your equilibrium, with your sum of moments. And this only comes through practice. We know that. You have to be able to identify the critical fastener really quickly. That's farthest from the neutral axis. You need to understand the loading distribution, that it looks like a beam in bending. And you've got to be really quick with equilibrium equations, which means practice, 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 so you don't have to think hard about it. And then lastly, look, there's no lookup required here. Not every problem requires a lookup in the reference manual. They gave you info that you didn't need. Tensile stress area, bolt grade, proof strength. We see this all the time. Extra info, trying to trip you up, making you go look for something you don't need to look for. All right, folks, that's it. As usual, thanks for watching. See you next time.